Okay, so for this video we're gonna deal with series of non-negative terms, which are a series just like this one, in which well, it doesn't matter if this is a 0 or a 1, right? Remember, in which the terms of the sum are all greater or equal than 0. Okay, for all natural numbers, every element is positive. Okay, so if we go for the partial sums as we saw the other day, so we have S1 is A1. Okay, so let me check this. This is not from 0, from 1. Sorry. So S1 is A1, S2 is A1 plus A2, okay, and then we keep going up until S sub k, which is A sub 1 plus A sub 2 plus blah 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 plus A sub k. Okay, so this is the sequence of partial sums. Okay, partial sums. Well, this is an increasing sequence. Okay, if we take S sub k minus S sub k minus 1, what we get is A sub k, which is greater than 0. Okay, so the difference between the two consecutive terms in the sequence is greater than 0, which means that this sequence is increasing, monotonically increasing. Okay, as we saw in unit 3 about sequences. Okay, so either this, so that means that the values of if you go from, this is n 1 2 3 3 and so on, and these are the values of S sub n, the partial sums. This is increasing. Okay, so there are two possibilities. The sequence of sums is bounded above, and then the sequence is convergent, right? So that means that this series will be convergent, right? Series from n equals 1 to infinity of A sub n is smaller than infinity, or it is unbounded. Okay, and in this case, this sequence, the series will be divergent. Okay, that means that this will be equal to infinity. Okay, and also, as we saw in the unit 3 of sequences, the convergence of the series will not change if we take any subsequence. Okay, so if we do from, let's see, k equals 0 to infinity of A sub n sub k, where n sub k is a rule by which you take elements here, the convergence of these subseries, or if you want, right, if you can think of as this subsequence of this sequence of partial sums, the convergence of this series will be the same, is the same as the convergence of the original series. Okay, so this is a fact that is very useful in computations, and we will use it in some of our demonstrations as well as proofs for some theoretical results. Okay. Okay, so now oh yes, and so furthermore, if a series is convergent, a series of non-negative terms is convergent, if convergent, then this series will be, we can call it A. Okay, and if we have a different convergent series, for instance like this, we can operate with them just like real numbers. Okay, because they are real numbers. Okay, so this will be A plus B, so you can sum them, you can multiply them. Okay, so that's a very interesting properties of this series, and this is because these series are they're absolutely or inconditionally convergent, but absolutely convergent. Okay, automatically. So if they're convergent, they're absolutely convergent. We will see what's absolutely convergent later on in the unit. But so far, just get the fact that if a series of non-negative terms is convergent, then we can operate with it as if it was a number, okay? Because it's a number, okay? So having said that, we now have, there's a lot of tools or tests to check if a series is convergent or not, okay? There are like a million of them because everyone discovers new ones every year, okay? So we will see some of them, actually 5 of them here, because I don't want you to get bored so easily with them. And with them you can actually decide the convergence of mostly every series that you will find.